Hey kids, man. No, I'm just kidding. I just really like that song. Welcome back. Today we're going to continue with what we've been talking about, what's a good proof and how we write it. Hopefully you've seen that there's different types of reasoning and problem solving that we're dealing with, where I might try some numbers to find out a pattern and then maybe later write it generally. So what we start with is if-then statements. If I had just say a statement in if-then form, we call that the conditional. I just made one up that if you are at least 18 years old, then you are able to vote. As you notice, my first statement is a hypothesis. You're seeing if you're 18 years old or not. And then you are able to vote. Now, what's nice about if-then statements is that if the hypothesis is true, we can then assume the conclusion is true if the original statement is true. So let's look at this. If you are at least 18 years old, then you're able to vote. Is that a true statement? Well, actually, in the United States, it's not. There's conditions that if you're not a U.S. citizen or if you're a convict, things like that, you actually can't vote. So this is not a true conditional. Then we talk about its converse, where what we actually do is flip the conclusion and the hypothesis. So if you're able to vote, then you're at least 18 years old. And actually, this converse is a true statement, because if you're able to vote, you went through all the stuff that you were a U.S. citizen and all that kind of stuff, that we can actually conclude that you are at least 18 years old. So you can stop the video if you need to, take your time to write down these notes of a conditional and a converse. But moving on, here's a visual of what we're going to call inductive reasoning. Inductive reasoning we use a lot in our real lives. As humans, we just do it all the time. And with inductive reasoning, what you do is you take examples or specific cases and you just blow them out of proportion. The example I like to use is stereotyping. A lot of us stereotype. It's unfortunately in our nature sometimes, but some stereotypes are true. I used to wear glasses, and to be honest, a lot of people would walk in and they'd see me in the shirt and tie and my glasses, and they'd say, "Oh, you must be the nerdy math teacher." Well, I'm not nerdy. I'm cool. But a lot of times we do this in math also. We see that, hey, a couple examples, I'm finding a pattern here, and then we find one wrong, and it doesn't work. And it's not a true proof, then we find counterexamples. And here's a classic example of this. This dude is the man. Leonard Euler, 1707 to 1783. I mean, just had his hand in all sorts of mathematical problems. But here's one of his most famous for inductive reasoning. And what I want you to do is actually do 5A through C. Okay? I want you to test some points in this n squared minus n plus 41 and check if they're a prime number. Again, a prime number being it's only divisible by 1 and itself. So you just plug in something squared minus that same something plus 41 and see if they are some prime numbers. And then try B, see if this actually is true, and then I think you're going to find C interesting. So stop the video for a second and test those possibilities of A through C. Hopefully you tried those. So you notice Euler didn't do so hot. He found everything worked up until when n is 41. And then we say, well, actually, that doesn't produce all the prime. So we actually look at this other reasoning called deductive reasoning. So inductive reasoning is finding some examples to find a pattern. But deductive reasoning is saying, you know what? I know these facts. I know all these definitions in math. I know some accepted properties. And what we can do is combine all these things to actually make new statements. So that's more of a where inductive is we're blowing it up, and then deductive focusing in on one little thing. So here's an example of deductive reasoning. And we've seen it before. If an even is written as 2n, that should say, and an odd is written as 2m plus 1, where m and n are any integers, we're going to prove that an even plus an odd is odd. This is what that would look like inductively. That I'd pick any even, 2, plus any odd, 9, and see that it is odd. So we do a couple examples, 4 plus 3 is 7. It looks like it's working out. Inductive reasoning is great to find patterns, because what you should be looking for in your inductive step is look for counterexamples. Try and find stuff that doesn't work. But if you see that the pattern's working, then we go deductively. Deductively, we have to use those facts we know that are true. They have generalities that say it always works for any possible. And we saw this in the previous video. So I'm going to add a 2n, that's my even, plus my 2m plus 1, that's my odd. And we're going to see if this actually is or produces an odd form. So a 2n plus a 2m plus a 1. Again, we cannot combine those n's and m's, so I just simplify. If I could add anything together, I would. But I have 2n plus 2m plus 1. Now, in both forms for evens and odds, we've seen that we need a factor of 2 somewhere. Sometimes it's just 2 times something, sometimes it's 2 times something plus 1. So let's still factor out a 2. You're going to see that's a common theme. What I'm left with then is n plus m. But then I have this plus 1. Well, since I can't factor out 2 out of that, I shut my factoring off. Well, done. And I add 1 to it. Well, look at here. This is the form of 2 times something plus 1, which is odd. Our number system says, well, if I get to an even, here's the even 2 times something plus 1, I'm at an odd. So I use my inductive to find the pattern. I use my deductive generalities to find the proof. Now, there is one thing wrong with this, where n and m are any integers. You have to have that. I can't plug in n as 0.5 and m as 3/4 and this still be an odd number guaranteed. So make n and m any integer. What I want you to do is you're going to solve these next two for your homework. You're going to find the product of an odd and another odd is odd. And you're going to show me, I want you to write it as inductive. Find some inductive examples and then do deductive. And the same thing on this next slide, if you need to stop and write it down, feel free. And then this is your second problem. The product of an even, oh, I had a lot of typos on this one, an even and an odd is even. Okay, I want to see the inductive. You only have to do maybe 3 examples of inductive. Just make sure the pattern's there. And then deductive. Okay, so again, as a recap, inductive reasoning is using examples to find patterns, but it doesn't prove something. It doesn't prove that it works every single time. That's where deductive comes in. If there's something that does work every single time, we should be able to use our generalities, use our math rules to prove it deductively. Again, have a great night, have fun, and see you tomorrow.